sort of CAD domain today, your design may still happen with the smooth or the BREP surfaces type representation that we saw in the early part of the lectures. And then, your applications sort of want to look at the surface mesh type representation. The applications could be additive manufacturing or rapid prototyping. That's one application. The second application could be visualization, right, and animation. And then the last, of course, is machining, right? So in all of these, then the mesh becomes a more useful tool. Okay. Now, I guess there is no CAD system still today where both these are present in the same kind of framework, right? But if you recollect, right, in the early days of CAD, the surfaces and the solids sort of proceeded in a divergent path, right? And it's only in the late 80s that they were brought together again into a single CAD modeling framework. Okay, and therefore, you should not be surprised if you see a CAD system that comes up with allows you to sort of look at the smooth, continuous models like the boundary representation or even just the plain surface models, and they are integrated with the mesh models, which are either triangular mesh, right? Mostly triangular mesh, because that's where the big advantages are both handled within the same framework. Okay, so that's, I guess, one possible direction. Right. What I want to do next today is to touch one topic that we missed doing when we were talking about surfaces. Let me just pull out the slides for that. Right. Okay. And that is this issue of quality. Okay. Now, don't have much material on this, but let me just start by saying what we mean here. Right, you have already been introduced this notion of continuity. Right. So when we talk about continuity of a surface, essentially we are looking at continuity of the derivatives. Right. So the 0th order derivative is continuous, the tangents are continuous, curvature is continuous, and so forth. Right. And we have also seen that there is a little amount of relaxation offered to the designers, right, where the application allows you to have so-called geometric continuity, wherein it's not so much that the magnitude and the direction are the same on either side of the junction, as in C1 and C2, but rather only the direction is maintained so that the magnitude not matching allows additional degrees of freedom to manipulate the shape of the curve of the surface. Right. So this is a little more relaxed constraint than the C1, C2 continuity requirements. Okay. So continuity, in some sense, is a measure of the, depends on the derivatives of the surface or the curve, right? But when we talk about quality, there is an attribute that is further over and above continuity, right? Because there are certain instances of surfaces where continuity may be prescribed to be very small, C0 also sometimes. You may have seen some of the newer cars coming with a crease on the body of the surface, right? So that's a place where even tangents are not continuous. But that is something that from a visual appeal perspective, perhaps it has been decided that is desirable. But the quality that I'm referring to today doesn't have to do with continuity, right? And what it has to do is with the notion of what people call fairness. Okay. Now, there's no formal definition to this, but essentially you can think of this as, the undulations in the surface. Okay. Now, you may think why we are making this distinction. The reason we make this distinction is that I can have a very wriggly surface, right? And yet a continuous surface, right? Your trigonometric harmonic functions are classic examples, right? As you know, they are continuous in as many derivative levels that you want to go to, right? Because it will keep toggling between cos and sine, and therefore they will always be continuous, right? And yet it may not be a fair surface as far as the CAD applications are concerned, because they have these undulations. Okay, so that is in some sense a very high level snapshot of what we are about today, right? That we are not so much concerned about continuity in terms of the derivatives, right? Rather, we are looking at a situation where, despite the fact that the derivatives are all continuous, I may still deem the quality surface to be of a poor quality from an application perspective, right? And what I'm going to do in the next 2-3 slides is to reflect on some techniques that people have come up with to decide when these undulations, how to track where these undulations are, and then try and fix them. Right now, both detection and fixing are manual. Okay, it is not automatic, which means that you, the user sitting in front of the CAD system, has to do both. Okay. So I will quickly go through some methods that are used and offered by the CAD systems, and show how they work, right, and the kind of output you get. But the fixing part is something that I will not address today, because this is something that is a skill-related issue. And of course, some understanding is required, but primarily skill. And that is something that we will have to leave it for you to acquire by working on such models. Okay, so typically, how do we detect these undulations or bad quality in the surface, right? I mean, a very sort of a simple way to look at this problem is, the advertisements that you see for these automobiles, right? A lot of these automobiles, you will see that the environment around them, is reflected on the body of the car. Right, so it is driving through a business district, and the buildings are all lit up, and that reflection plays off the surface of the car. Right, and in a very sort of overview kind of manner, the undulation detection essentially is by the distortion in that reflection of the image. Right, so if I have a very undulating surface, then a reflection of the environment of the car body, right, is something that will show up with a lot of breaks and kinks, right? Whereas if my surface didn't have that many undulations, then the image, the reflection will just wrap over on the body of the car, right? That's roughly the idea that works between a lot of the reflection-based techniques. Okay, I'm showing you one here, which is known as the zebra plot. Okay, and these are coming under the category of a technique called isophotes. Okay, the idea essentially is this, that I have either a sheet of light or a line of light, and I sort of plot the reflection of that sheet of light on the surface. Right, so if I have, let's say this one may work out to be very smooth, but let's say if I have a light like this, then it'll sort of bend like that if I don't have that many undulations, right? And that will tell me, okay, that this is some bend that I want in the surface. But if there was a small kink or something in the surface, then you will see that as a small wriggle here, right? So if you have small kinks and other things on the surface, then it will reflect in the form of these light reflections on the surface, and that will tell you that I have a problem with my surface, right? So essentially, what you do is that you have a surface and ask the system to generate what is known as the zebra plot,
and it will give you these plots. So as you can see, between the first two images here, right, the sort of grossly the zebra plots look the same, but you can see that there are a lot of wriggles in the zebra plot locally here, right? There are additional bends. There is an overall bend in the surface, which is okay, right, as you see here as well. But if you see that other than that, the lines are looking very sharp and crisp. And so this will be deemed to be a better surface than a better quality surface than the one that you see on the left here. Okay. The actual background to do this is essentially, reflection, right? So projection of a line on a surface and then, reflecting it back. That's essentially what happens here. And so the wriggles in the surface will cause these lines to get, further wavy or wriggly. Whereas if the surface does not have those wriggles, then you get nice crisp lines like this, even though the lines themselves bend, right? So what was originally a straight line from the source, right, gets bent because of the surface, and you get to see this. And so that's how then you will improve. You can go back and improve the quality of the surface in these locations till you get the kind of surface that you want here. Okay, and there are other examples in this, right, to sort of do this. This is actually from a paper where they compare, some other techniques as well. But the point that I want to leave you with is that, the generation of the plot, which is the focus for this thing, how the plot is generated is the focus in the paper. But for you is how to interpret that plot, right? And then go back and fix that. So as you can see wriggles in the surface here, and then you can fix that and get the other surface. Okay. Likewise, let me see if I have the other picture, because you would have already seen that. I don't think I have it here. Oh, okay. You may have seen this other technique. I had used this picture earlier. I forgot to copy it here, called the curvature comb. Okay, let me just see if I can open it here, because that was one of the earlier techniques to do this. So let's see, I think it was in the surface. Here, there you go. Right. So this is what is referred to as a curvature comb. Okay, and again, this is generated for the curves that you input, right, by the system. And essentially what it does is that at every point it plots the curvature, right, the direction and the magnitude, right, and essentially draws up an envelope around that so that it looks like a comb locally, right, these lines jutting out at some frequency. Now you can, so the curve is not zoomed in so much detail, but what this plot shows immediately is that there are some dips and valleys locally as you move along this curve, other than the larger, smoother dip and valley that you see here. Okay, and that's what is shown in these broken up combs, right? That locally I have some, a break, even though the curvature is sort of continuous, it is smoothly varying, right? There is no problem. Nowhere do you see that the curvature sort of goes up and comes down like that, right? It is rather smooth, but nevertheless, it is because of the wriggliness of the curve underlying, this kind of variation is not acceptable, right? And therefore, the curvature comb is another way for you to sort of pick out the variations in the quality of the surface. Okay, and a similar sort of an idea is used for detecting quality with slightly better results, is instead of having light. Okay, so this is a hood of a car, right, on which you are projecting the thing, right? Typically, what we used to use is, lines of light, right? Sorry, this should be parallel. And these are projected on some underlying surface, and then they are drawn. So here I have lines in the other direction and some in this direction. And so I plot them on this surface. So you can see that what should have been parallel lines, sort of get bent
and moved around depending on the deviations, undulations in the surface. Okay. And so it gives you some information. You can go back and try to fix that. Instead of lines, if you use circular lines, right, instead of rectilinear lines, what we do is that we treat the light source to produce on a plane thing instead of actually the lines here are not in this direction. The lines are in this direction. Sorry, right? So on the same kind of hood, let's say I start with planar circles of light and I project them onto this curved surface. I get an image that looks like this. Okay, the resulting reflection lines or projected lines are looking like this, right? And therefore, immediately, you can sort of see that, where I am having some, local kinks and breaks in the surfaces, undulations that I have not anticipated, right? So I may have a crease in the middle of the hood here, right? So I do expect to see a break, but I don't expect to see, sort of a kink like that. So I need to go back and do something about that. Whereas these look okay, where there is only one direction it goes and then comes back. So here it is sort of going up and down. So I need to fix that. And elsewhere, if there are some deviations, you can make out and fix them. Okay. So essentially, what the trick here is not so much in the technique, because the technique is coming from the system or the tool, but the sort of the challenge here is for the designer to go back and fix those details in the underlying surface that gets rid of this. And that's the huge task. You see, in real life, the model maker would use sandpaper, right? And basically touch the surface up so that some of these details are straightened out, right? But in CAD, right, you are dealing with control points or any other way that you might have defined the surface, and you have to move them around to get rid of this, and that's the real effort. And unfortunately, there is no formal method to that. You will have to do this. Acquire this by repeated generate and test kind of a paradigm, where you fix it, go back, generate the plot again, see if you are happy, otherwise come back and fix it again, right? So that's the only issue here, but otherwise this is what you do for evaluating the quality of the surface. Okay, so you can see here the difference you see, in a relatively smooth surface, right, without any undulations, etc. You get these nice circular lines projected onto the surface, right? Depending on where you started from. So maybe this is, sort of a vertically, the viewpoint is somewhere from here, right? But here you can see that there are some, dents or depressions, right, which, while smooth in terms of the derivatives, right, are not good in terms of the quality of the surface. So you can see these undulations captured here in this region corresponding to the bad quality that you see here. Maybe a hammer fell on it or something like that. And so you need to go back and fix this on your surface so that you get a circular plot that looks like this. So that's the challenge. Okay. We actually don't have that many. I mean, in Alias, we used to cover this. This time we could not. Let's see if we can combine you with the next batch. If that life, is a different classroom scenario, we will try so that you can get to see this. Otherwise, you can check if there are material on the web where people actually have videos of how they do this. It might be instructive, but the problem is this and the tools are this. Okay, fine. So I think that's as far as the quality of the surface is concerned, and that pretty much brings me to the end of everything that I wanted to say. There is one other thing that I wanted to expose you guys to, but I need the help of one of my students to do that, and I'm trying to get him. So if, and that's about a new a new paradigm in some sense, you can say, called generative design. Okay, and so the idea is to sort of generate designs using patterns, and so you have, let's say, a simple hexagonal hole, and you sort of use a tool to generate patterns of these hexagonal holes and get some interesting shapes. Okay. That is just an example to give you a picture of what there is in this, right? And the reason why this has now become popular is because of, again, 3D printing and additive manufacturing, because some of the shapes that you get to generate using this technique usually cannot be made otherwise. Okay, so for example, right, if I have a simple L bracket, right? Now if I want to optimize this, right, then I may only play with the sizes typically, right? I'll only play with these sizes. I can make them small or big or thin depending on the kind of stresses and other things that I get, right? But it may turn out that if I can, do some very interesting things to this shape, right, I may get a very optimal shape that looks like this, right? And I'm just doing the 2D part of it. I shouldn't have extruded it. So I may get some shape that looks like this, right? Or I may get some shapes where I have in the inside of this also some cavities built in. Right. Now, these are not some things that you can make through your existing manufacturing techniques, but you can make them through this idea of 3D printing. Okay. Of course, it is not easy there as well. There are only some techniques that can allow you to do this, and there are some issues with that as well. You may study it in your subsequent classes, right? But at least they are feasible in this process. So these techniques have come forward now to exploit this thing, because you would like to have, a very high strength to weight ratio for the part, right? So one way is you can use materials with very high strength, but the other way, more interestingly, is to reduce the weight. And reduction of the weight is possible by using porous structures. And generative design seems to be one good way to generate these porous structures. So if I can get, and there is a tool that has now come up which allows you to sort of visually create these things called Grasshopper. So I'm waiting for my student to sort of offer this. So if he is able to do it, I will ask him to do it on Wednesday. But otherwise, maybe some other time we can I'll arrange for a demo for you, right? And other than that, pretty much I'm done with everything that I wanted to say in this class. So I will stop here and just say a couple of things organizationally. So I will be available on Wednesday as well if you want, to sort of, I've lost my window where I was talking to you guys. Yeah, I found it. Okay, so, I'm available for any questions or topics that you feel were not done well and, needs to be revisited. Then we can take advantage of the 1 hour on Wednesday to do that, right? Otherwise, I will request my student to give you a demonstration on Grasshopper so that you get exposed to that technique. And then we just have to plan for your turning in the assignments. I just saw one issue. I'll request Kumari to sort it out. I'm seeing only 4 assignments, though the numbering has gone to 5. I couldn't find assignment 2. Is that the case, or I just looked at the wrong place? Do you know if you have 5 assignments? With the 5th one being a bonus one. Anyone?
Yes, sir. We saw one bonus assignment.
Yeah, but other than that, the bonus assignment, you have only 3 assignments given so far, or 4 assignments?
That I'm not sure.
Okay, fine. So I will ask her to check that. So, but anyway, the last one on the reconstruction is a bonus one. So, which means that it just gets added to whatever you get, but the total remains the same, right?
And I will ask her to check if the remaining are 3 or 4 so that everybody knows that. I think a lot of people have turned in the earlier ones, but finish everything if you can before time. And you need to inform me for the slots for the exam. As I said, in the normal times, we would have 3 quizzes and each on one of the topics, so that the final is always on the solids, but we have 2 in between, one on curves and one on surfaces. Now this time we have finished the one on curves, but not the surfaces. So either we can combine the 2 and have a 2-hour exam, which can front as the final. Or if you wish, we can have 2 quizzes, then you need to give us the dates for the middle one. The last one, of course, will be held as per the timetable that the institute has given us. Okay. So that's everything that I had to say. Like I said, if you have questions, you can either send me mail or, and I can answer, or we'll meet again on Wednesday and you can tell me another day and I can come up on Teams another day and address any questions or doubts. Materials are there under files, at least till curves, I think, or surfaces I'm done. I'll add the other ones also now so that they're all available to you. Questions? Yeah.
Sir, about the last assignment, the bottle and the glaze, the issue, I tried it, but my computer couldn't take that much load, so I dropped the assignment.
I see. Can you just send a mail to me and Kumari? I'll find out if we can find a lighter weight model. We didn't think of that. Okay.
Yes, so that will
if there is a lighter one possible, then we will try to put that in.
Yes, so actually I thought it was the small piece surface. So as soon as I opened that, my system.
No, maybe because they have loaded the entire things, but there could be the surface could have been scanned in 3 or 4 sets. So maybe we can just give you one of those sets. Yeah.
Yes, it is the whole bottle and
I know.
crown.
That will be heavy. Yeah, that will be heavy. So just send us a mail. I will see if we can segment it out. Yeah.
Sure, sir. Thanks.
Yeah.
So also, during that session, Deepak introduced to one set of tools. When I Googled in Google, I saw one software called Power Surfacing SolidWorks, which was meant only for this purpose, like meshing and smoothing out the curve. Yes, so if we could just get an introduction to that software, that looked more easier than this.
I see. No, I think the reason is that could be a paid module. Let me find out. I'm not very familiar with the tools, so I will just talk to these guys and then I'll come back.
Yes,
PowerSurf, is it?
Yes, it is really expensive actually. So
no, I know. That's probably the reason why we do not have it. But I will just check and see if at least somebody can talk about it. I will find out. Yeah.
Yes, just one introduction so that we can
I'll find out. I'll find out. Yes. Yeah.
Sure, sir. Thanks.
Okay. Yeah. Any other questions, comments? Okay, if there are no other questions, then please track this team. Your messages to me as well as our messages to you. I think we'll probably keep it here. So watch out for any changes in the assignment as per this comment your colleague made. We will see if a change is possible, then we will send it. And the dates for the quiz, if you want 2 quizzes, please talk amongst yourself and then let me know. Otherwise, I will plan it as 1 2-hour quiz on the day, whichever it is, I will announce it here. Okay. And any other questions, comments, you please let me know and we can meet here on Teams. Fine. If there's nothing else, then we'll meet again sometime. We'll definitely meet for the quiz and we'll meet again after that as well. So good luck. Thank you very much. Yeah.
Yes, sir. Thank you very much.
Thank you, sir.
Thank you. Yeah.
Thank you, sir.
Thank you. Yeah.
Bye.
Bye.
Bye, sir.
Bye. All the best, guys. Yeah.
Thank you, sir.
Yeah. Be safe.